Well, it looks like we can start. It's officially week 9 for this class. Welcome back, folks. Well, week 9's special because we just survived midterm week, so I'm going to just assume the others are probably in recovery mode. Maybe we'll get some more in. But we're going to go through these notes here, finalizing the problem on doing the regression analysis, then move over to the psychology experiment problem to see what other new ideas we can get into. Really, the first problem was more about just looking into the inner mechanics of working with R. And now for the second day, the psychology experiment, we'll do some actual honest inferential statistics using the raw data provided down here in the sample. Other things I want to mention before we get started is the recordings are all going to fall in this folder right here. So if you click on that, it just takes you to a playlist right here, just the one video from last time. And aside from that, I don't think I have too many more major announcements. So I'll return it to the class. Any questions or comments so far?
I don't have any.
Okay. Well, I'm thinking for day 2, we're going through the psychology experiment, but again, kind of a late start on it while we finish off this problem up here. And I'm thinking on day 3, what I'll probably do is post a problem where we have a really large data set. We have to work with the actual, forgot what that was called inside R. We have to work with the actual data frame structure, subsetting functions to really see key elements inside that data set. So a different kind of take on what we've been doing so far on day 1 and even on day 2. But let's get started on what we were doing. The indented files right here are just where we left off on. The files that are non-indented, those are the ones that are just blank. And so here's where we left off on. We took all this information we saw in this picture here, imported it in this way, and this is just a screenshot of our RStudio environment at that point. Then we wrote out this syntax down below, and so that takes us to this part right here. There's all the syntax where we left off on, and now let's see what we were doing. We imported the data set, just the points from the scatter plot. From here, we plotted the data just to make sure things look about right. Oh, I ran the whole code. Then from here, we constructed the model. We specified we want a degree 4 polynomial, and that's the curve that's been sketched through here. By calling linear model, it's going to be y tilde is a way to say regressed on a polynomial with degree set to 4. And right here, I actually made a mistake. I need to put this one to true. Let me see if I can describe why. So let's delete that, retype raw. Then RStudio pulls this back up as a reminder what raw does. It says, if true, use raw and not orthogonal polynomials. This one defaults to false. It is using orthogonal polynomials, which is okay. They plot just fine. But if we're going to integrate this to actually find the area of the property, that was our main objective, we don't want the orthogonal polynomials. We need to set this to true. So that was the first mistake in the syntax. It's also duplicated down here, but instead of typing this in, I'm just going to re-overwrite this with our finalized syntax. So setting that to true, after doing all that, this line takes the model itself and plots out that curve that we're seeing down below. And then we just ran out of time when we got to this spot right here. Coefficients, short for coefs, short for coefficients. We called the function coefficient, or coef, refers to the model. And that was stored in this location right here, the entire regression analysis. So if we rewrite down in the console down here, COEFFS, that is telling us all the coefficients of the polynomial. The intercept was 326.11. The degree 1 term is negative 420 times x power 1, then minus 161 times x power 2, and so on. So from all that information, we can now build out our polynomial function and integrate it right inside here in RStudio itself. So that's just a fast rundown of what we did last time. Any questions at all, folks, about any of these steps or the correction here? Okay, well, let's now go down into actually building the polynomial itself inside RStudio. What we need is to define a function. We could call it, say, poly, if you'd like, but that's a function itself. So let's go poly f. So now this is all our own. Polynomial f is going to be getting the result of a function. So this is a big structure inside RStudio. I need to say what the arguments or input to that function is. Because it's just going to be a single real number, we can say function x. Then next thing we type in is curly braces, hit enter, and usually I leave one right here, right after the function starts, and a curly brace terminates right here at the very end. At this stage, we're really building the actual polynomial function itself. What we need to do is say, let's take something called result. It's just an intermediate function. When we're done with the function definition here, we'll return whatever the result is. So return just says we're doing some computations inside here, and whatever that result happens to be, we pass it back to the function x. This is going to be its final definition. And the blue colored coding is a way to convey all that. So our result will be, give it COEFFS, or however we decide to specify it. Or if I do that, I'm giving it all of the coefficients. Not exactly what I want. I need to build these out term by term because what we're trying to build is this all together. P of x, that's the polynomial function, is going to be a naught plus a1x plus a2x squared plus a3x cubed plus a4x power 4. Kind of tedious to build all that. But I'm just doing one step right here, specifying the constant in this polynomial function. So instead of calling all of that, we can do it this way. If we just want one part of this variable, COEFFS, that's a vector from 1 to 5, you can type COEFFS 1. What that does is it just gives us our first entry, the intercept, 326.1, or looks like 1 repeating. So go like that. And now we've got a function. Not the whole function, right? This is just the very first term of the function. But at least we're getting there. And here's what you could do if you want to work really hard. Go plus COEFFS 2 times x. That's the next term of the function, and we can keep on tacking these on. But just like we observe over here on the right, that's tedious. What if the polynomial model was degree 40? We'd be here all day, and we're probably going to make tons of mistakes. That's just too much typing out for humans. So let's actually backtrack on that. What we really want is a new structure called a for loop. That's just going to append all the coefficients to the right power of x all on its own. So let's design a loop to make that happen. Loops? Well, you probably would guess they should start with for, and that is right. This will be the for loop. Let's look into the structure. It says, kind of a weird structure, honestly. For should start with a parenthesis. It should say something with the index. I think that's what the $sign says. Well, it might make that index like a I. We'll go from 1 if we choose to start to something else with that we'll specify. So here's what we'll do. We'll say for parenthesis. I is going to be our index inside the for loop. And I is going to go from, let me take another check in my syntax. It's going to be I in. That's kind of weird. That wasn't really something I actually saw there when I looked into the help on that. But it'll be I in. And now we'll go 2. The reason we're starting at 2 is we already have the first result for that coefficient, which is going to be coefficient 1. So we need to go to coefficient 2, the very next one, to get the linear term. So we're starting up in 2. The colon says we're going to increase by 1 integer. So we'll go to coefficient 3, coefficient 4, until you sweep through all of the coefficients. That means we need to end at degree plus 1. But let's wrap that around even more parentheses to be really specific. This is how the for loop is going to be indexed. It'll be indexed on I, starting at 2 and going up to 5 altogether, because there's really 5 coefficients. Notice the mismatch on indexing. This is the standard way to write a polynomial. First term is indexed at 0, and then 4 more terms. So we have to manage that disconnect on the indexing versus the way RStudio indexes all at the same time. Kind of annoying, but great way to think about the for loop as we go. Just as we did with the function, we use a curly brace to say, here's what goes on inside the for loop. I'll leave enter right here to have this the start, excuse me. And down here, this is where the for loop is going to end. It'll return the result of all that looping, and then that's the whole specification of the function. So now we just need to say what happens with the rest of this. We already have a result where it's a constant polynomial at this point. So we'll go result gets result, then add something new. So we're just tacking on a new term, storing it back inside result each time we loop through just the for loop inside this. So what should this be? Well, we're trying to put in the very next coefficient. So that will be COE-FFs. Put in a bracket, I. Because recall, the bracket is how we index into the vector structure and just get a particular element. We need the second element. So that's why we're starting off in 2, going up to the degree plus 1. That's going to give us this right here, the second coefficient, negative 420.2. Then we multiply this by x. We really need that times there, or RStudio doesn't know what to do with juxtaposition. It interprets that literal multiplication, which is shift 8, as the multiplication function. We need to give it a power. So we'll go power I. But actually, that's not right either. This is what makes this problem kind of frustrating in the middle, navigating through here. Anyone see where the mistake is on this line? Kind of hard to see, right? I would say the mistake on this line has all to do with this spot right here in particular. That exponent is wrong, and we don't get that exponent just right. When we go to integrate under this polynomial curve rather, we're going to be getting some wild results. So we need to fix on that exponent I. I itself starts at 2. That's how our indexing is working inside the for loop. But when we're at 2, we're picking up the negative 420, the second coefficient. It goes right here in what we would call A1 as a polynomial function. And the power has to be 1. That's where the trouble is. We throw I right there. The power starts as power 2. Now we have the wrong coefficient. Well, if we go I minus 1, then we're in business on this. Because when I is 2, that's to the power of 1. And when I goes up to the final thing, degree plus 1, well, degree is 4, we'd be at 5. That means we're using the 5th coefficient. We'll go on the 5th term, and then finally, the power has to be 4, so we just subtract 1 power. That's why it has to be a I minus 1 right here. So we're nearly there. This is the polynomial function. Let's run it. Hit Control A, Control Enter. Let me clear the annotation. We have a function down here, but honestly, this isn't too descriptive. If I click on this, it's not going to show me the polynomial function. It's just going to show me the actual definition of the function itself. It is designed as doing an expression like this, running through a loop, and then outputting the result, passing it back to the function. So, well, that's not super informative. But one way we might decide maybe we're on the right track is, let's do an output of this function. Go poly f, put in an input. We're doing an input to this function, so we'll use function notation with a parenthesis. Let's put in a value 0. We plug in 0, that means we're wiping out all of these terms right here. It's not the most perfect check, but it's a good one, because p at 0 should be a naught, which is the constant term. What happened here? Constant term, which was 326.111. So let's try this out. Poly f at 0, 536.927. That was not what I was expecting. Let me see here. I might have a mistake on this. Something went a little bit awry with my coefficients. It's in scientific notation out of nowhere. Let me see what happened. COPEFS. The intercept is now 5.3927. Which would be 536. I'm doing the scientific notation on that. And yeah, that is the right value. Somehow, some way, it looks like RStudio threw scientific notation at me out of nowhere. Made it look like we had the wrong thing, but we're on the right track with this. So I should have noticed that exponent right there, telling me that was really the actual right number. I think it just ran out of space in this environment. So it's compactifying things down a little bit more. Okay, we've got a polynomial function, and now we're going back to this. The whole objective of this problem is to find the area of this property, which is really an area under the curve type of a problem. We can make RStudio integrate this immediately and see what happens. But before we get to that, a problem like this should always involve a sanity check first and foremost. So let's do the sanity check first. Then we'll integrate inside here and see if we're in the right ballpark of what our expectations even would be. So this is the sanity check. We were going to do nothing special and just tell people, here's the approximate area of this property. We might have visualized it like this. One gigantic right triangle. And if we were visualizing it that way, we would have said the area is 1/2 times the length of the base, 400 units. I think this is measured in feet, times the height. Looks like that's at, I'm tempted to say 600, but let's go 540 to give an even better approximation. So we're expecting an area in this ballpark, about 108 feet squared. I would say the true area is much bigger because of the way this right triangle is approximating. It's a slight overestimate up to the value of 100 feet, but then a major underestimate for all the rest of these values. So keep your eye on that number right there. If we've got the right area, it should just be a little bit bigger. Not twice that size, not half that size, that's going to be in the wrong direction, somewhere in that ballpark. So we built the polynomial function. Last step here is integrate. And this is kind of nice. All you had to do to integrate in RStudio is define the function in their way so that RStudio knows what it's dealing with. Then just go integrate, pass it the function. We named it poly f, poly underscore f. Tell it the lower bound of integration. We can read it off the diagram. Lower is 0. Upper value is 400, way out here. And now when we hit Control A, Control Enter, this should solve the whole problem. So this is the moment of truth for us. Just trying to make this a little bit bigger. Well, let's hit Control A, Control Enter, and the area we got is about 30,000 feet squared larger than when we took a look at it with our sanity check, just the area of the right triangle. This actually looks like it's the right amount of area. It integrated numerically, think trapezoid rule, Simpson's rule, all that interesting stuff. And so it's telling us the error making that estimate substantially small, so it's pretty trustworthy as a value. Well, that's the whole problem, folks. if this ever happens to you in your life that, say, someone wants to analyze an area problem given information that's essentially a scatter plot, RStudio is a pretty good environment for taking that on. It's actually a pretty small problem, but the way that we wrote out this syntax is really dynamic. Give it any data whatsoever, call it X and Y. If it's a humongous data set, we'll have to use this function right here to import it. That's what we're going to do on our next problem. Then decide on the complexity of your model right here, run this entire syntax, and everything changes along with it. So all this is incredibly dynamic in that sense. But to finalize the problem, let's put the right syntax right here. I've got a little bit bigger. And let's call this the solution. Maybe let's put the warning above. Or maybe under. Let's say about right here. Okay, just try to get it down to one page. So the whole answer to this question is that syntax in RStudio. Kind of a weird way to answer the question, but you can just grab it, copy it into RStudio and run it, and it provides the answer down below. And like we mentioned, you can also run a whole bunch of scenarios now. What if we want to estimate its degree 1 linear? Here's what we would get. Notice it's a better estimate than even our ballpark figure, because the right triangle goes this way now. So not exactly the right triangle, it gets cut off right here at the 400 value, but that's a way better estimate. We can now run even more scenarios, look into degree 2. Our estimate changes to this area, close to the official answer we gave. We see the change in the model, and we can scroll up to look at other features of the model. For example, we were discussing this element right here. Adjusted R squared tells us about 86% of the variation in the y coordinates themselves are being explained by the degree 3 polynomial, which might make sense on why they asked us on this problem to do degree 4. Well, that was degree 2, rather, not degree 3. Jump to degree 4. And now it tells us in degree 4, close to 100% of the variation in the model has been explained. And this is the area that we produce as a result. Well, we got it, folks. This is the end on the regression analysis. Any last questions or comments or follow-up thoughts getting through all of that syntax there? Okay, well, we've finalized this problem. Let me save these notes here. And on the Moodle webpage, not sure what I was trying to say there. On the Moodle webpage, the solutions I'm just going to re-upload here. So the blank problem is above, solutions down below. And now next thing we're going to get into is a psychology experiment. That always sounds exciting. First in RStudio, since I'm done with this environment, a couple things you might want to do is wipe out everything here, because you never know when something stored might conflict with the new syntax you're about to write in. One way to do it is just click a button, the little broom here symbol will do the job. I honestly don't know what the include hidden objects does. I just check it each time. Seems like a good idea. Environment's gone. It's important to clear the plot history, but if you wanted to, you could. And now we have a fresh environment. Let me also even reset the script. So now, after all that's done, let's go back inside here. This is just my thumb drive, which is duplicating what you see on the Moodle website. And here's our psychology experiment. Well, we have some data, lots of descriptions of what's going on, and a practical research question down below. Let's first just start by absorbing all this context. We're told research has shown that people are more likely to show dishonest and self-interested behaviors in darkness than in well-lit environment. Now we know we're really dealing with a psychology experiment. And keep in mind, when it comes to psychology experiments, we have a bunch of students being used here as participants in the experiment. However, they were not told what the actual experiment was at all until the whole thing was concluded and they leave wherever they were in the testing room, for example. So no one knows what the real problem is here. They go on when they're participants in this psychology experiment to be given a set of 20 puzzles. Notice how it says we're talking about self-interested behavior. These people were paid 50 cents. That's not a great pay rate, but they were paid 50 cents for each one of those puzzles solved in a 5-minute period. So now there's an incentive to work clever and work hard. However, the participants were reporting their own performance. So again, this is the self-interested behavior. You're grading your own work as you solve the puzzles. And there is no way for the experimenter to come in and check their answers. That's what the student would have to perceive when they take part of the experiment. No one's actually watching. Thus, the task provided a clear opportunity to cheat, reserve, and receive undeserved money. But that's not the whole problem. The problem is about self-interested behavior in darkness versus a well-lit environment. So they even took this further. Hopefully, when they grab these students, they, by randomization, plug them into one of these two different treatment groups. One of them was in the dimmed room, and the numbers that you see here is just the correct number of puzzles that was solved, self-reported. Always remember that part. Second was in a well-lit room, so think really, really bright lights. And this is the number of correct reported, self-reported correct puzzles solved. Looking at the data, it does look like the dimly lit room did a better job. Keep in mind, these are different students on the left column, a whole set of different students on the right-hand column. And the question we're being asked is, do we have significant statistical evidence of a difference in performance between these two lighting conditions? So that's the whole statistical problem. Any questions about it? Okay, well, this is the statistics part of it. It's really hard to do a problem without doing a little bit of statistics. But at the same time, we don't want to get bogged down on statistics either. So this will be just a really fast sketch of what we're about to do to address this question right here. First, we state the parameters we're about to estimate. We'll let mu W, referring to an average in the well-lit room, and mu D, referring to an average in the dimly lit room. Let's say let mu W and mu D refer to the number of correctly solved puzzles recall, don't forget, self-reported. Or I kept saying students. We don't know exactly that these were students, but in a university setting, it most likely would be. I'll just rephrase this as participants. For participants in a well-lit and dimly lit room, forgot how to spell room, let me fix that, respectively. I love the word respectively because it sets up a one-to-one correspondence between UW being the well-lit, UD being the dimly lit room. So we wrote out two sentences at once. And to attack this question right here, really we set up a set of hypotheses. The null hypothesis is the claim to be tested. And this would be a claim of no effect going on whatsoever in this population. That these two, oh, forgot one big word. Don't forget, it's the average. This is the mean of the population or the average of the population. Let's call it the average number of correctly solved puzzles. And in the null hypothesis, we're assuming it's going to be the same in both groups. There's really no difference in these two different populations. Versus an alternative hypothesis. This encapsulates the research question. Is there a difference in those actual averages? So we would test mu W not equal to mu D at a certain level, certain threshold of evidence that we're going for. I'll specify it to be a high threshold, 0.01. So this is the statistics behind all of this. Now we take all the data, import it to RStudio, and attack this problem right here. Sorry for this part. It's kind of hard to do the problem without saying what's going on in the background. But now, here with RStudio, we're ready to go into the forward process and actually analyze the data. First thing we have to do is import the data. This is the file that's provided on the Moodle website under those new diagram documents on the psychology experiment. And if we really wanted to, we could redo what we did on our first problem and just directly type these in. You might write in well lit, C 7, 8, 10, all the way to 5, and then close a parenthesis there. That's working way too hard. So instead of doing that, go here, download sample and put it in a location that you're going to be able to access really rapidly. I put it in my thumb drive in folder math199, so here it is under sample. Once you have it downloaded, one really nice feature of RStudio, not R itself, but for the IDE RStudio, is it streamlines the process of importing data, which is sometimes really nasty inside R if you have to type this in directly. Here we can point and click, go with the first option from text base, then just point wherever that file is. I'll set it to sample. Under name here, you can leave it as sample if you like. I'll call this puzzle because it reminds me of the context. This is about solving a number of puzzles and self-reporting. Down below, it shows the data. If I scroll just a little bit, all I need to hit is import. And we've got it. We have a data frame. It's called puzzle. And the $sign is a way to say column 1 is the well lit. We also see it over here under above the console rather. Here's the puzzle data. Well lit is the first column, dimly lit is the second column. So that alone is a big upper hand with RStudio because it actually takes a lot of work to import data like that. There's a ton of syntax here. Then after all that, I usually just click this away. I'm usually looking over here. I'm not as worried about the preview it provides. Well, any questions at all, folks, on the data import side of this so far? Okay, let's go on to the next step of the analysis. We're trying to address these hypotheses. Then usually what we would do is select a test that we think can handle them. This has 2 independent samples, so t.test should do the job for us. But when it comes to statistics, everything has conditions. Really, the first thing we're going to do is see if our conditions would be met. So we're going to visualize the data to check conditions. And there's lots of ways to visualize the data. One plot could be the histogram, or another plot could be a box plot. Let's go for the box plot. Just call box plot, pass to it puzzle, so the entire data frame, and this should work out for us. Hit Control A, Control Enter, and there's my box plot on the right, but I have some problems with my graphics. Let me see if I can expand this a little bit. That looks a little bit more like box plots. I have a pretty limited resolution, so my graphics get kind of compressed here. If you're in the same situation, click on the export button, copy to clipboard, and then you can just resize these things in a slightly better way. So here's our first graphic. And you know, it's kind of an interesting scale, right? These are box plots, so we have something to say about them. We have the well-lit column and the dimly lit column. These are the 2 treatments in the psychology experiment. We have a scale running this way, but you know, you should specify the description for every scale. Anyone happen to know what the context is for these numbers here? What does 6 through 14 have to say about anything in this problem?
Are Are those the questions that they answered correct?
Absolutely, good call on that one. I think that's actually kind of tricky because we might have thought of that as a horizontal axis, yet in the box plot, it's going vertical. So let's add that description just as you said. With any kind of graphic like this, if we want to make a modification on the y-axis, we call this y-lab, short for y-label. See what that tells us. Nothing. That's kind of not helpful. Let's keep on going. For y-lab, the y-label, we're going to set it equal to some value, but we're passing to this a string, so we have to start by doing quotes first. And let's say number of self-reported puzzles. I'm running out of horizontal space, so I'm just going to hit enter and keep on typing. So this is just a way to keep it all in one window so we don't have to scroll horizontally to see the whole syntax. If you hit enter right here, RStudio just reads past all the white space till it gets back to this spot. So let's see the modification. Control A, Control Enter gives us something here. Let's see if we can fix it. Hit export, copy to clipboard. And, that didn't work out too well at all. Puzzle solved. I was hoping that would get a little bit longer. How about we say here, self-reported puzzle solved. What I'm trying to do is just trying to contain the size of this to see if I can get it to fit in. And it might have something to do with the window I was providing with it being really narrow. And no, nothing happened there. Maybe it's because of that break I put in. Didn't think that would happen, but you know, weird things can happen sometimes when you're doing something in front of everyone. Say hit Control A, Control Enter here. And yeah, self-reported puzzle solved. Strange. I'm not too sure why the behavior did that on me. If I go like this, it should have continued. You know, I see weird graphic anomalies here and here. I almost wonder if it's strange. It almost feels like it's putting text to the far left, but glitching out in the weirdest way possible. This is a new one for me. I might have to come back to this and figure this out on my own. But this will be our workaround. Let's just shorten the label so it all shows up. Now you can either hit export, copy to clipboard, copy plot, go back here if you're thinking about writing out a report in this kind of way. And here's our first graphic that we have so far. Some concerns here. We show that the data is trailing off to the right on the upper end, majorly on this group. On this group right here, the middle line is M for median, or the 50th percentile. This line right here is quartile 1, or the 25th percentile. This is quartile 3, 75th percentile. This is the max. This is the minimum. And same discussion over here, almost. Let me fix my penmanship first. Except there is a bit of a problem. This has been flagged as an outlier by the 1.5 IQR rule of thumb. So 1.5 IQR just means IQR itself is quartile 3 minus quartile 1. It's the interquartile range. And this value is more than a distance of 1.5 times the interquartile range above the third quartile. It's just too far away from the main grouping of data to call it typical. That's an abnormal observation right there. So that's what the box plots tells us. And the outlier is a concern. Apparent skew is a bit of a concern, which means we should probably include even more graphics on this. Let's take a look at this from the point of view of histograms itself. So Back inside here, we want side-by-side histograms. So let's write out par MF row equals C1, 2. What this is doing is splitting up my graphics field into a system where I will have one row, but two columns altogether. So I'll get a histogram for one variable, a histogram for the other variable. And here's how the histograms could come in. Go hist, puzzle, except that's not going to work. This is going to give us a syntax error right away. Notice those curious dollar signs, however. If we type $, we have an ability to select whichever variable we're trying to work with. Let's go with the well-lit first. Then go hist for histogram, puzzle, $select, the dimly lit room. And this should give us the side-by-side displays that we're going for. Here they are. This is the outlier that was flagged by the box plot. And both of the data have skew to the right since the observations trail off on the right-hand side. We have some weird issues that we want to correct with the actual naming of these, and probably down below here as well. Notice also, vertical axis is different. This is frequency. Horizontal axis is number of puzzles solved. All this is saying is there's 3 students between 5 and 6 puzzles solved because the frequency was 3 here. It's telling us where our data aggregates. But let's also write in here par MF row equals C1, 1. This undoes the side-by-side displays. So if we do something down below, the graphics over here on the right behave as normally. And let's change the main titles here. This is just clunky, right? Histogram of puzzle $ well lit. If people saw this published in a journal, an academic journal, they would probably just cancel their subscription right there. That's showing poor care on producing those graphics. So for a better main title, we can go main equals. Let's just call this well lit. Or I guess I'm calling it well lit room. Similarly, down below here, let's set the main title to dimly lit room. And here's the change on the right. Well lit room and dimly lit room, that feels a little bit better. This is saying what are the independent populations that we're dealing with, the categories. We should fix these labels as well down below because this just doesn't look that great. Puzzle $ well lit. No one is going to know what you're talking about unless they use RStudio themselves. So we go XLab for the X label. Oh, now it shows up. Usually RStudio is good about saying what this is. This will be equal to, let's say, just something brief. Puzzles solved. At this point, the reader is going to have to use the context that this was self-reported puzzle solved. Then next, same value, xlab equals puzzles solved. So here's the change on the right, hit Control A, Control Enter. And these are slightly better looking graphics now. You can resize these however you like. Just click on the export and then use this to resize. And you could use the copy plot button, but oftentimes Windows Shift S to get the snipping tool out is a little bit better because you're not carrying in excessive amounts of white space, which RStudio is known to do a lot of. Drop that into the document. And let me try again. Thought I took a screenshot. You know what, I'm just going to do copy plot. Seems like it's a little bit more robust. And here is the plot copied in. Now this outlier that looks pretty concerning was at 12 puzzles solved, maximum excluding the outliers at 10 puzzles solved. And looking at the data from 9 to 10, one student is in there just barely at the upper value, 10. This is the outlier, but it really doesn't look too extreme so far. In fact, what's going on well for us in this problem is both sets of data have the same shape. That's good for the statistical procedure we're going to use. They're both skewing to the right. And no outliers seem to be really influential here. This was just a rule of thumb that RStudio generates. With our extra view on it, that's not very extreme as an outlier whatsoever. And so now both sets have the same shape. What's the size of these? Said observations, 9 of them, but that means 9 for each group altogether. So there is n equals 18 observations. That's a pretty good sample size for our t-test to be robust against any outliers going on. It looks like the conditions for the t-test are met. So conditions for t.test are met. I mean, there's a lot more to talk about when it comes to these conditions, but from the point of view what we're trying to achieve, just show how to use R for some analysis right away, we don't want to go too long into this discussion. This was more about producing those graphics just to see how bad they are. Now we're going to address the original hypotheses by seeing how reasonable the null hypothesis was. We assume it's true in hypothesis testing, do a little bit of work computing a test statistic, and find the probability of getting the data we actually got. These data were expressed down here. This is pretty extreme. We'll find the probability of getting data as extreme as that, or even more extreme, under the assumption the null hypothesis is true. So this part right here is the inferential statistics side of everything. When we do the inferential statistics, we want to pay really close attention to our hypotheses. It was a two-tailed test because of the not equals right here. And that's the standard test. So RStudio is just going to run it that way. But at a significance level, alpha is 0.01. We also need to set one thing additionally. A confidence level should be set to 0.99 because we're also going to produce a confidence interval all at the same time. And I'm not too sure what it's saying there. I'll just click that away. So let's go t.test. We'll throw to it puzzle, $select, the well-lit room, the one we specified first. Not that you have to set that first, but if we set that one first, it means we're thinking of this one as being the first parameter on the left. Then go puzzle, to select the dimly lit room. Next thing we throw in there is we need a confidence level at 0.99 because the hypothesis test is at this benchmark of evidence, 0.01. We are looking for a probability, a p-value, that's below that. And if it's below 0.01, we have evidence the alternative hypothesis is true, that these population averages are actually different, and we'll give a 99% confidence interval for the estimate of the difference itself. So put in here, conf, for confidence level, 0.99. And last thing to say is alternative. It is two-sided, and that is the default, which means we don't actually have to change anything here. But it's not a bad idea because if we had a greater than or less than sign, here we would need to specify that. So just to be really specific, let's just say 2.sided. Let me double check the syntax on that. Alternative. Retyping it so RStudio can help me out by pulling this up. It should have been 2.sided in quotes. That's the default thing. So now let's run this whole thing. And here's our output. We have a p-value that's 0.002. That means we in fact have a high degree of statistical evidence that this right here is true. The mean of the averages, not the sample averages in this data, but the population average, if we tested everybody, is really different from the well-lit room and the dimly lit room. Now, it's up to the psychologist to say if this is evidence of self-interest behavior. I mean, maybe in the dimly lit room, you just thought you solved the puzzle right because you can't see the details of the puzzle too well. Who knows? But we have evidence of a difference, and this is the estimate of that difference altogether. Loads of stuff to say once again about this, but because we're running out of time, sorry, seems to be really hard to get all the thoughts in at once. This is where we're going to leave the problem so far. I have about 10 more minutes of discussion about this one on this is statistical significance, so we want to talk about practical significance. But I don't want to talk about this problem too much more when we come back next week. Next week, it's going to be more about having a gigantic data frame right here and doing some exploratory data analysis and some subsetting to produce these kinds of graphics when there's a lot of data happening. But again, I'm sorry for breaking this problem down in the middle, not finishing it off entirely. Any questions at all, folks, with the analysis we've done so far?
No, I'm good. Thank you.
Yep, absolutely. Well, once again, these are all going to be recorded. And if you have any kind of questions about this before we come back next Tuesday, don't hesitate to email. I'll be happy to discuss this a little bit further. There's so much to say about these kinds of problems that I'm tempted to finalize this syntax once we come back next Tuesday. But before we come back next Tuesday, I also wanted to put in just a little bit more information here in the middle. So if you're curious about the statistics itself, you'll have more information there. And then this will be our main result down below once it's finalized. So let's call this solution so far. Again, sorry for running over a minute again, folks, but this will be where we end the class for today. Next time, we'll finish off this and look into handling a gigantic data set next. Well, have a great afternoon, folks, and I'll see you all next week.
Thank you.
Yep, you bet. Take care.